particular, I think these tenors is important when we have this, I mean, interplay between lecturer and DC, but also horizontal between DC and DC. I think it's quite a peculiarity. I think you are lucky to have this European network having this opportunity, at least. For me, it's the second experience because we had a similar one with Poema and was quite successful. Okay, the title, I have the mouse. No, what happens? Something bad? Maybe because the mouse was in the bad point. Oh my God, sorry. Angelos helped me before to, if you don't mind, view mode.
It's a bit hidden.
There should be a written presentation somewhere, no? But
it's a bit hidden. It's here. Duck, and then go. No, don't close it. Just put it on the background. Just click here.
Okay, now works. Sorry. So we have this tensor product. No, okay. This is one of the basic spaces we have to study. And when I say space, I think it's important to have some geometry inside. So geometry means for me that you have some relation which should be independent on the coordinates. Still, we use it's not modern because comes from 19th century Klein approach that you have a group which acts on a space, and everything you want to write down should be invariant by the action of the group. The group I choose today is the orthogonal group. Why? Because I want to study distance function, and this indeed is still modern object because optimization is all based on distance function. Indeed, I think you will see in my slides many things already present in Bernard slides and also in Monique, maybe from a slightly different point of view. Okay. Among the possible distance, I will choose the scalar products, but there is a guiding principle that if you have a group action on each individual space, no, then the product of the groups act in a natural way, component-wise, on the tensor product. Be careful that we saw that these are just building blocks of the tensor space. And all the other elements are sum of these. But when I prescribe the action on the building blocks, so on the decomposable, and in all the other elements, the action is prescribed by linearity. So the action on the sum is the sum of the action. And this is the basic principle that works in vector space and extend to tensor and works very well. Okay, I will tell more about this. So try to have a general, well-known framework. I call a vector space Euclidean if there is a scalar product. A scalar product over the real just means bilinear form, symmetric, positive, definite. So just the classic Euclidean form. And now when you have this form, you can take the norm, which is the square root of the scalar product, and this norm square is a distance in a slightly, abuse of notation. Of course, the distance is the square root of this. But when we compute the critical points of the distance, which will be one of the main themes giving the with the goal to have a minimum and maximum of some function, then it's the same thing to consider the square. And this has algebraic advantage, of course, because it's a polynomial and the square root disappear. I agree if there is some criticism that in these two sentences there is a slight abuse of notation. The distance should be the square root of this, but take in mind what I tell you. And now in this framework, my basic question is the following. If the individual space VI are Euclidean, so you have a metric in each of them, I want to make the tensor product an Euclidean in a natural way. And the answer to this question is positive, well known, and there is a way very natural to make this. This equation 1 is the requirement that I have. So recall each VI as a scalar product, and I call QI. You see the QI are here. And I want to compute a new object. V double V is called Bombieri-Weil. The new scalar product, Bombieri-Weil, should have this property that when you apply to a decomposable tensor VI on the left and another double VI on the right, then the result should be just the product of this individual. There is a theorem saying that such a thing exists, and if you think a bit, it is not obvious, because this requirement looks at first glance very, very strong, because all elements in general have a not unique decomposition in the composable. So if you have a tensor, which is the sum of many of these, you say, I can apply linearity, and then by linearity, I can prescribe what is the solution. But you could have another expression, you apply linearity in the other expression, why at the end you get the same thing. So this condition obviously implies uniqueness. So if you ask this, which is very strong, you have a unique solution. This is obvious because if you prescribe over the decomposable, all the other are some of these, and then you prescribe a unique way. But the existence is not obvious, anyway it's true. Anyway, it's true. And there is, well, a easy way that you define the orthonormal. Oh, sorry. I was already jumping to the next slide. Give a bit granted that this exists, then you have consequence. One consequence is that the norm of the decomposable square is just the product of the norm. Okay. Another consequence, when you have orthogonality, and here there is a feature easy but important to underline, that the necessary and sufficient condition for two decomposable to be orthogonal is just that exists one index when you have one vector orthogonal to another, because in the product it's enough that one is 0 and all the product is 0. Okay, so it's not necessary to ask for all of them. So in some sense this is quite a weak conclusion, but of course it's something you have expected, because the vector space given by the tensor is very large. So you should have many orthogonal tensor to each other. Remember this, which is important. And also the requirement that, as I told before, if you act with the product of orthogonal groups, what I defined here is invariant for all the products because each of them is invariant individually. And now the usual solution, you fix orthonormal basis of this. So you fix something non-canonical, but can be chosen in each of them. For example, fixing this is equivalent to have a standard Euclidean form in each of the spaces. Sorry, I see there is a typo. This should be VI, because it's the index I up means the vector space, and the lower index means that you have the basis on such vector spaces. Then you see, you change all the index, one in vector first vector space, 2, 3, up to k, which is the last one, and you declare this is an orthonormal basis of this, and then is an exercise to see that if you change basis according to orthonormal properties, so if you act with the orthogonal group, what you define in this way is well defined and it is invariant. Doing exercise, of course, is important. Now maybe I missed a board to show you something, and in the web page of this learning week, I have posted an exercise sheet, which is supposed that you can try to do and maybe collaborate in trying to do exercise together. Okay, this I already said, these orthonormalities. Okay, let's just maybe underline that prescribe a scalar product is equivalent to declare that some basis is orthonormal, of course, because then you prescribe all the possible. So orthonormal, I means different elements have a scalar product at 0, and each single element which itself a scalar product 1. And then you have prescribed all possible product, and then by linearity you prescribe everything. Okay, up to now you see the theory is quite boring. No, you have these, and at the end what you get is the usual expression, essentially as a sum of square of the coordinates. This is the expression of the norm of any tensor up you fix orthonormal basis, and there are no surprises. This is the unique invariant product. Well, and the name Bombieri-Weil indeed is maybe not enough justified in this context. There are other many names people call L2, in the sense you have the like LP space in L2, you have this Hilbert, maybe Euclidean, some people call Frobenius, but be patient. In a few slides you will see that this requirement will create some less boring and more interesting situation. Okay, this is still boring, but it's useful to understand. Is the first non-trivial case. What happens for tensor with only 2? You know, there is a joke that God created the matrices and the devil created the tensors. Because when the number of factors increases, there is a qualitative behavior completely different. So if something works for matrices, you have never the guarantee that the same thing works forever. And let's show why this happens. The reason is group action. So when you have only 2 vector space, you have a group acting over, which is given by what is the dimension of the group orthogonal or GL on each of them is more or less asymptotically goes as the square of this one plus the square of the second dimension. And if you have 3, you have another square, another square, another square. So the size of this is the product. So it's again like a square. If they have the same dimension, it's again a square. But if you have 3, it's a cube. So it's much bigger. It's qualitatively bigger. And if you have more than 3, even more. You are losing the naive setting of the square dimension, and you create something much more complicated. So remain in the setting created by God, and you have these decomposable elements. Well, they are well known. They are just rank 1 matrices. And here, the name rank introduced by Alessandra, is the same as the rank of a matrix. It's not a different thing. And now the exercise, and this is really an exercise in the exercise sheet. If you have 2 matrices, what is the Bombieri-Weil product? Is the trace of A, B transpose. And I think this was also defined by Bernard. And you see the square of a matrix is the trace of this. And note that this is a positive definite symmetric matrix. What I ask as an exercise is this a consequence of just this condition. So if you prescribe what happens on rank 1 matrices should behave in this way, and then you want to, by linearity, extend to any matrix, the only solution is this one. And in the exercise sheet, there is a hint to make this exercise. And just note that, for example, this is important. If you do A transpose, it appears on the diagonal exactly the sum of squares of any row with the corresponding column. And so when you make the trace, it's exactly the Euclidean classical behavior. Now, this is well known, but it's important to see this just follow from the previous rule. Now just assume that if BI are Euclidean, we see that this is in a natural way Euclidean space. And you see, you can even forget the positive definite, assume you have a signature, and use
What's some kind of typo there?
yes, there is the
You have QI.
It's not a typo, but it could be a typo. But in the sense that this is considered as a form, and this is the signature. Of course, this is an integral different from it. I use the PQ without thinking. You're very good, Guillermo, usually, and to check the stupid notation that I have used here, but forget my almost typo. And why this is true? Because this means that you have the same expression with the number you can apply to an element up to action that has pi plus 1 and qi minus 1. And then when you take the tensor product of these matrices, here the plus come when you have 2 plus or 2 minus. And here when you have plus minus minus plus. So this was the idea, just to show you that you can even extend to any tensor such a rule. And oh, God exists. Thank you.
It came fast, but it's small.
Thank you, thank you. You see how efficient his pen was. This was done by purpose, of course, but please, question. The previous slide, I'm happy to.
Was the distance that these are defined over the reals, or would it be a generalization to have the emission conjugate, for example, the A module squared?
Good question. So, what I said is defined over the real, but the same definition works over the complex without conjugation, and this gives the Bombieri-Weil that you can use. There is a variant of this when you have the conjugate, and this is no more bilinear, it's sesquilinear, no? It is the scalar can take away usually in the first component, but conjugate in the second, of course, because you put there. Here there is a difference that you don't act with the orthogonal group, but you act with the unitary group, which is a real group, it's not complex group. So in some sense, you create something more difficult because you have to work with the real algebraic geometry and not with complex algebraic geometry, because you have a real group instead of a complex group. I will have a few slides later, and the two things are both interesting in the sense that if you use this over the complex, you are computing some complex solution to a real problem. If you do the other, the problem is changing because you have always a positive definite because it's a real distance. Should call Hermitian. No, that's the name for the distance. But they are in some sense two separate words. Each of them has its own techniques. I think it is more studied for the geometrical point of view, the one without conjugate. And with the conjugate, it creates more problem. But for example, as you saw in the talk by Monique, in quantum entanglement, physicists are interested to put the conjugate. Okay,
But the distance could be defined.
Could be defined, and well, to try to be precise in. Oh, sorry. I was going in the opposite direction. This rule is true if this is Hermitian and you have a sesquilinear with a complex conjugate. You still ask this one, and still this works for the Hermitian norm. And this is true if you apply here unitary instead of orthogonal. And there are, of course, there is a main difference that it's difficult to have a higher form on with the conjugate, but still the exercise works, and this remains true, and this formula remains true if you put a conjugate here, and of course also here, no? And the differences now is a positive definite Hermitian matrix in this case. Okay, thanks for the question. I will have a slide later about this. I've not forgotten. And okay, now I start the part of the lecture which will be less boring and maybe less well known also. So you remember there was a debate when Alessandra told what are the symmetric power of a vector space, and the answer were just they were polynomials, and the title introduced scalar product on polynomials, which are SO invariant. So this means that if you have an actual of V, this same action extend to the symmetric power, in which way, if you have a G here, and here you have VD goes in the power of this linear form. And again, if you define for this by linearity, you can define for each other. This is a group, an element of the group, and this works also for GL. Now I choose a coordinate such that the expression of the orthogonal is just the identity in the in this coordinate system, and then this is just a notation which is useful. Is a notation very well used working with the polynomials. The so-called, when you write down a polynomial, you write as the sum of a monomial. So a monomial x alpha means x0, alpha 0, x1, alpha 1, up to xn, alpha n. No, now I'm choosing that the dimension of V is n plus 1.
Do you choose alpha to be d factorial over alpha factorial d minus alpha factorial, maybe?
No, it's correct. This is the multinomial coefficient.
The definition.
Yeah. Yes, that's correct. It's the multinomial coefficient. It's is d factorial divided by minus alpha. Of course, the sum is d. So I said the partition alpha of d, just meaning this one, okay? And this is the coordinate expression of that, no? I said that VD is the power of a linear form, and you can expand all the coefficient in this way. That's quite important. Is a rank 1 symmetric tensor, such thing, no? Okay, now that's the theorem of above in the symmetric setting. You recall before there was a requirement on the composable element, you have the product of all of them. Here the situation is easier because the product of two decomposable just introduce v power d, double v power d. And this is again the requirement. The product of all of them is just the power of a single one. And you can repeat the same objection I said before. It's not obvious that such a thing exists, because it's true that any polynomial is a sum of these, And this restriction, this condition, obviously imply uniqueness. So there is a unique product satisfying this. But why it should exist? Because this case is well known that we have many different combination. Let's do just a concrete case. Study SIM5 C3. This was studied by Hilbert, more or less in the same period when he produced a paper cited by Monique when you have a sum of squares. Here is odd, so you cannot have sum of squares. But Hilbert proved that the general F here has such an expression, sum 1, 2, 7 of Li5. I think I am correct because 7 times 3, you see it's 21, which is exactly the dimension of the space of quintics because it is 7 to 2, yes. But this is not unique. And if I'm not mistaken, there are 5 such minimal decomposition. Non-trivial result proved by Hilbert. It's quite interesting if you read French, as many of you here, since we are in this. Hilbert wrote a paper to Monsieur Hermy, famous professor, and the letter is Mon cher Monsieur Hermy, je suis, and prove this just in a few lines. And then it was considered so important that Hermy said, maybe we publish this, okay. So it's published in Journal Mathématique pour Appliquer. And if you see, if the paper begins, Mon cher Professor Hermy. And well, now apply that. You have F is the sum over Ij of Li, Lj power 5, defined according to that. But since you have 5 different, if you change and you take another with completely different called Mi, you have completely different scalar product, but they match. They have the same. So this is a very restrictive, behavior. And now the solution that was found in 19th century is really smart. How you prove the existence of this? Where you use apolarity. So you fix, as we say today, an orthonormal basis. And for any polynomial, you apply a differential, you construct a differential operator, defined by P applied to the partial. So essentially, you change what you have if your P is x0 cube plus x1 square x2, P tilde is just delta 0 cube plus delta 1 square. So it's just the same polynomial that becomes a differential operator. This is the dual ring of the other. And then the rule is the following. If you want to construct a PF, you perform P tilde applied to F. And to normalize, you have to divide by a scalar, but this is not important. And you see, for example, what happens in the monomial basis. Well, in the monomial basis, this just means differentiate the second monomial by the partial of the first one. And so they are orthogonal, but not orthonormal. That's an important feature. You see, even if you divide by this is the universal and comes exactly the inverse of the multinomial coefficient. But in this way, you can construct everything. And there are a lot of computer algebra systems doing this. Let me recommend that if you use Macaulay 2, exactly this operation works pretty well. You pick two polynomials, you write diff, the first and the second, and you get the apolar product up to this scalar factor, which is a way to construct this one. And now maybe the exercise is a bit complicated. This is what I just said about Macaulay 2. This also answers a bit your question. Even on symmetric, the definition works as well over real and over complex. But now there is a difference that over the real, there are no polynomial of norm 0. The polynomial of norm 0 is called isotropic. On the complex, you have. And this is even a large variety. It's an hypersurface, which is a smooth quadric. So the expression is the following. If you apply diff, if you write F as a sum, D choose alpha, F alpha, X alpha, then the norm squared is sum D alpha, F alpha squared. And this is what comes from the differentiation. You see, it's not a typo. This is not squared. Appeared only. So you cannot square this. You have to multiply by the inverse of the alpha. But you see, it is an expression which is, in some sense, Euclidean with some parameters. And in the coordinates F alpha coordinates in sim dv. And this is a quadric. Note now, you cannot say these are orthonormal coordinates. It's not true. There are these coefficients, and this is a usual trick that make easy to do mistakes doing computation with the polynomial, but come from the requirement as before. And there is a guide, a complete alternative characterization of the Bombieri-Weil product, which is given by another formula. You see what happens when you apply the product of any polynomial with a rank 1, so with the power of L. And this was taken as an important property by Bernard, that it's evaluation. So you evaluate F at L. And let's do okay, a proof. So the proof is nice. It's just 2 lines, you see. Because also F has a sum of powers. So you can try first to take also F of rank 1. And so it is just the differentiation of L power D with M power D. And this is by Leibniz rule. It's obvious, no, that if you if you have a differentiation of a linear form at power d, you take d and you get, well, maybe let's do. So assume you have some differential operator of degree 1 at power k, no, at power d, and you apply with LD. So you have first application, you get d LD minus 1, and then a scalar. A scalar delta L is obviously a scalar product, is exactly the evaluation of one form in the other. And then if you do again many times, you find the d minus 1, so you have d factorial, and then this scalar is repeated exactly d times. And then if you expand f as a sum of powers by linearity, the property is true for every, because you see this equality is linear in f. And note is not linear in L, is linear in LD, because this means evaluation. So the expression contains L at power d. Okay, that's beautiful and makes two different points of view about Bombieri-Weil. And now that we have seen the importance of V versus V dual, take this isomorphism from V to V dual, which is given by V sending to QV blank, no? That's the usual way. You can extend taking second symmetric power for the second symmetric power of V to the second symmetric power of V dual. So where goes Q? Q's going the Laplacian, and in the orthonormal coordinates, the Laplacian has the usual expression, well known, but this is a geometrical object. It depends only on the metric. So if you fix a Euclidean structure on V, there is a unique Laplacian. And why this is important? Because again, exercise, the space killed by the Laplacian is invariant. You see, the Laplacian takes sin d, since it's a differential operator of degree 2 in sin d minus 2. It is easy to check the Laplacian is surjective on the image. And so this kernel has dimension given by this minus d minus 2. Let me write also that. So with this notation, the dimension of the harmonic is n plus d, choose n minus n plus d minus 2, choose n. Why 2? Because the differential operator decreased the degree by 2. So this is invariant subspace, and this makes a difference. Before, when we have just a V1 tensor VD, this was irreducible. Now this is reducible. So it's reducible as a module over the orthogonal group. It is irreducible with the action of SL, because this is no more invariant if you just act with any invertible matrix. So the philosophy is that the Laplacian is a metric object, and so it's important in this situation. Harmonic polynomials in any optimization procedure are quite a thing to be underlined. So the symmetric space splits in the space of harmonic and its orthogonal. And now I want to describe the orthogonal, and this is what I do in the next lectures. First, lemma, you can ask, since are so important, the powers will be when they are harmonic. And from what I said before, it's easy to check this formula. The answer is that the harmonic one are the isotropic ones. And if you compute the Laplacian of these, it's an exercise that you get this formula. So it vanishes exactly when QLL vanishes. And indeed, you never see any of such phenomena over the real, only over the complex. And now, of course, as a consequence, you get a thing well known in functional analysis, that when you do such a thing, in some sense, the Q and the Laplacian, so the quadric and the Laplacian are adjoint, in the sense that in a scalar product, if you have a Q on the right, you can put on the left and becomes a vector, you see. And then, as a consequence, this means that if something is orthogonal to the Laplacian when this is vanished, well, this means it is zero. And then if this is harmonic, is orthogonal to everything which is multiple by Q. So it follows this orthogonal decomposition. In the complement, you have, in the complement of harmonic, you have polynomial divisible by Q. Okay? And let's give shortly the proof. Again, you see, I try to do the proof with less computation as possible. We already saw this, and this is essentially enough. Now the time flies, so I'm not sure if I have time to follow all my proofs, but I have to check that this Q can be taken on the left, no? And essentially, here you are computing what happens here, and this is evaluation, and so it is evaluation of QG. You create this, but this is exactly the result of applying the Laplacian to delta D. No, I take on the other side. So it's practically obvious without computation, and this is an interesting fact. And now try to use the geometry. How you can describe an harmonic polynomial as a sum of powers? You can, but they are now sum of powers of isotropic vectors. And this is just spanned by all of them. I think I skip the proof, you can believe. There is a property of the quadric, which now I have no time to underline. And the consequence is that this is already irreducible. And the proof is that the orthogonal group acts transitively on this variety. So you see, you have this quadric embedded. The quadric is usually embedded in PV, no? But let's do the Veronese embedding. If you take V to VV, this is the Veronese embedded that was defined by Alessandra, and you go here. This is called the Veronese B. Then you get the Veronese image of the quadric. Now, this does not span all, it spans just the projective space of harmonic polynomials. And here I'm saying that since the orthogonal group acts transitively here, and that this is invariant, it's not possible to have an hyperplane here which cut this, because you should have already some subvariety of the quadric which should be invariant, but over the quadric, of course, the orthogonal group is transitive. So you get, as a consequence, this result, which is maybe the easy but non-trivial, that is not possible to have an harmonic polynomial which is multiplied by the quadric. Even on the real, I think it's obvious by what I said before, that there was an orthogonal decomposition, but on the complex they require proof, because there exists isotropic vector. So you see the left is trivial, and why also the right side is clear, because the statement is equivalent to prove that the subspace of polynomial divisible by Q intersect the harmonic only in zero, and otherwise, since both are invariant by the orthogonal group, this, if it is non-zero, should be an invariant subspace and contradict irreducibility. So you get this. You see, this is a linear system in F, if you forget this. And the only solution, this means that is a square system, non-degenerate. It's not the identity, of course, the Laplacian of Q. It's more complicated, but and so harmonic decomposition, we use this. We have, let's say, already a name. You can decompose uniquely any polynomial in such a way that you get F, let's write here what happens. So with that notation, you have F0 plus Q F1 plus Q square F2. And then, of course, it's finite because we have a finite dimension. And no, sorry. Here I use different notation. Sorry. This is called FD. This is called D minus 1. And here's, sorry, D minus 2 and D minus 4. So, of course, it's a better notation because each polynomial is indexed by its degree. And this is called the harmonic part. So try to see how you can find. You given F, you want Fd. So you do the following. Let's show you it's better. You see, I reverse this. Fd is equal to F minus Qg. And now apply the Laplacian. You want this is harmonic, so you want this is 0. This is now a linear system in G. And the homogeneous linear system has only the trivial solution because I proved before. And so for any Laplacian of F, this has a unique solution in G. That's so you find this, and then you can iterate, and you say in the harmonic part of G is Fd minus 2, and you can find again and again and again. So it's just iteration of linear systems, and you can find your harmonic decomposition. These behave well over the reals, in the sense if you compute the harmonic part of the conjugate is the conjugate of the harmonic part, and of course as a consequence it preserves reality. Even since everything is canonical, if you have a vector bundle, which is a family of vector space, and then you compute the symmetric power of the vector bundle, and you have a Euclidean form in each fiber, this is a subbundle. And you have a harmonic decomposition as a direct sum even of that. That is called an orthogonal vector bundle. And maybe it's important now to write down what happens in the splitting case. Look, this is different from being decomposable. I'm just computing L power D with the product of linear forms. And the answer is that it comes the product of the scalar of L with Mi. And this is interesting because it gives a relation with the permanent. So if you have the product, a polar product of two splitting forms, the expression you get is similar to the determinant, but with all plus. So this is exactly the permanent of the Graham, which is pretty nice. Maybe let me skip the proof. And now, a bit of surprise that there are other orthogonal scalar products different from Bombieri-Weil, and that they give some other interesting computation. And here I describe all of them. You remember, first Bombieri-Weil asked that this product was equal just to this with I equals 0, and that this disappeared. They were not. Now you see that the number match, even if you apply V and double V at the norm separately, and here you have to put D minus 2I, and now this equation, this request is homogeneous in V and homogeneous in W. Everything appears the same number of times. And how you find, now we have this new tool of the Laplacian, and we can use in the following way. You have a P and F, and you want to compute such a thing. You apply the Laplacian I times to P and I times to F, so you decrease, and then you use Bombieri-Weil on the forms that you obtain after applying the Laplacian I times. It's clear that this is invariant again, and this written here is stupid because I should compute what happens with this new, and with this new, the monomials are no more orthonormal. Sorry, I have to correct this. I did it, but okay. But you see, there was, what's the philosophy is that my space in D is not irreducible. It splits in several pieces due to harmonic decomposition. Well, of course, you can have a Bombieri-Weil on each of them. And what I'm defining here is essentially a linear combination of each of them. So you can have choices that you don't have in the previous case here. This is pretty nice. And again, there is a proof, but I was too optimistic in my time. And let me skip, and you can read because the slides are available. What is important, and you get a classification. So all the bilinear form which are invariant by this is SOV, there is a unique, now it's not a product, SOV is a linear combination of the one defined before. And the proof use representation theory. You have to compute the product of the harmonic spaces. And it's just a trivial consequence of the Schur lemma. Again, I have no time to enter into the details. Let's do some comment. This Bombieri-Weil is non-degenerate, but the product that you first applied the Laplacian and then Bombieri-Weil is degenerate, is non-degenerate only on a sum, which is given by a piece of the filtration. That's interesting. But the general linear combination is non-degenerate. And all the linear combination of these coincide with Bombieri-Weil on the harmonic part. Why? Because if you have at the harmonic part, you have two polynomials which are harmonic, then you apply the Laplacian, you get to 0. And then there is anything else when I is bigger than 0. It remains only Bombieri-Weil. And this put what I did in a bigger context. There is a big theorem called the first fundamental theorem of invariant theory. This is all 19th century achievements. They proved that if you have an invariant for the orthogonal group, they should always be a polynomial in these three basic things. And you see, this is the norm of V squared, this is the norm of double V squared. And what I defined was just a polynomial here. And any possible polynomial is a combination of this one up to have homogeneity in V and double V. So it's, in some sense, the first fundamental theorem make down-to-earth concrete for such a case. You see, if you have a Macaulay 2, you define Q, and this define a formula that compute all the scalar product I define changing I. So you first differentiate F, you first differentiate G, and then again you differentiate all this. Then a proposition that the Laplacian respects the harmonic decomposition. So one summand goes exactly in the next one. And again, another property, since we have all these scalar product, you can ask if all the summands are orthogonal, and this is true. This is pretty easy, and I prefer not to bore you with the details of the proof that anyway is easy, because to prove this, you can reduce to this particular form of a polynomial which is in the closed orbit for the orthogonal group. This is the I mean, the idea to use geometry. Sometimes you read in the book quite long proofs, but with this trick you reduce to a shorter computation. And let me also comment why in the 19th century they wanted to write such a word in the composition. One of the main reasons was just computational, because if you write f in this form, all the computation through f becomes much, much easier. You can differentiate, you can evaluate, and evaluate a polynomial in this form is much easier. You just evaluate the linear form, and also compute the differentiation. So it was a very modern motivation. A consequence of what I said before about orthogonality is that the Pythagorean theorem computes the norm as just the square of the harmonic parts. And up to some scalar, this is just the norm of Fi, because this just computes scalar. That's very nice. Maybe I did not tell also another important thing, that in two variables, this is our Fourier expansion. So the harmonic decomposition can be considered as a multi-dimensional generalization of Fourier expansion. Now, come back to the real, and in the real case, not only the non-degeneracy by linear is important, but the positive definite. So the cone of all the invariant metrics have a structure that can be so it's a polyhedral structure. It's a cone in this way, and the edge just correspond to the summand of orthogonal decomposition. So they are degenerate, and Bombieri is inside, is an interior, lies in interior, because it's not degenerate. This, I think, reminds also computation done by Monique, no? That computed at the beginning how you can decompose in a sum of squares, and he got a segment. A segment was a polyhedral cone in that particular case. Let me skip the proof. And this is a remark which is computationally important, that if you have two summands, so in the harmonic part, this is really Bombieri-Weil in that part. So essentially, all the other products are constructed by Bombieri-Weil, interpreted in each summand.
So regarding this conic application, so it means that the membership oracle in the code is linear programming?
Yes. Yes, because you can describe the, I'll call it the extreme edges, and then it is linear programming in each of them. But should be not a surprise, no? It's a semi-definite thing. Yeah, because you have the request to be essentially semi-positive on each of them, and that's enough. It's a convex combination of the to be semi-definite on each of them. I think they are orthogonally, probably the fact that they are orthogonal is important in this. Now, at slide number 33, I satisfied the question arrived in the first minutes. You see that you can define a unitary invariant product. So I think I already commented and there is some technicality here about the conjugate, but it's quite natural. You can still call a Hermitian Bombieri-Weil product. And this is, according to the unitary, is irreducible. There is no Laplacian which is unitary invariant. The Laplacian is orthogonal invariant. And indeed, here there is a geometric proof that again, instead of the quadric, you have the sphere. This is the real sphere. But also in the real sphere, you have a transitive action of the unitary group. And so the same proof as before gives the irreducibility. Let me skip the details. Now, a very, very strange thing about the binary case. This, I think, is not so well known. Because happen essentially in what I said in the Fourier case in one variable, sin d of C2, you have a particular choice of the coefficient, which is unique, and you see with alternating sign. A particular choice in the interior of the cone, because this cone works even in two variables. Two homogeneous variables means one variable non-homogeneous. But works only when d is even. And you see in this binomial coefficient, you have to divide by 2. This expression is not only orthogonal invariant, but even SL2 invariant. Recall that SO2 is just a poor object, is just a system. So it's a torus. It's very simple, and this is much, much larger. For example, the first non-trivial case is d equal 4, and they were called classically anharmonic quartics. There is a quadric of anharmonic quartics. This invariant was called I in the classical invariant theory, and gives another interesting point when the computation can be done with this bigger group. Why this is not so well known? Because it's not positive definite, of course. And this is the signature. The signature is as much as you can close to half-half, you see. And indeed, for example, there are no anharmonic quartics with all 4 points real due to this, while exist for the other classical invariant, which are the harmonic, which are much more well known and can be all reals. Anyway, here there is the, computation by hand that show, you see, is a polynomial, which is that's the wedge product essentially that gives. Let maybe say differently. This is if you write down with the real angles, this is 1 minus cos square, so it's a sinus square, and so it computes the area. It's essentially like a oriented area of the two vectors. I wanted to put in a slide. And now some thing which connects this, what I did with analysis. So in book in analysis, there is a well-known scalar product of function, not only polynomials. I start now with the Hermitian thing, and you find that this expression, you have f and g, you take f, you multiply by g, and you integrate over all complex numbers. And in order to have, to be sure the convergency for polynomials, you have to multiply by some exponential. And these behave well not only for polynomials, but for all the functions which have a polynomial behavior. At infinity, this converges. And there is a feature of this product. This is a unitary invariant. But now assume that they are polynomial homogeneous, then they descend to the projective space. And it is beautiful that this is just up to a scalar multiple, the product with this, with the Fubini study method, which is a unitary invariant again. And why? So this scalar is chosen, is non-trivial just to have a normalization. And this sentence is important. This product coincides with the Bombieri-Weil defined algebraically, just because they are both a unitary invariant. And there is only one. So you see that computing integrals, which is a priori a non-algebraic operation, gives a surprising consequence just using a group action, that you have a unique unitary invariant. And as an exercise that I skip, you can do with the monomials. I did a lot of mistakes, and I hope that they are correct. You know, there is a famous book in quantum mechanics when there is an appendix with all this formula written by Feynman, maybe. And all the formula were wrong in the first edition. And recently, they were rewritten. It is written. There were 300 typos, so quite. And I bought the book because I remember then when I tried by myself, I did not understand anything. So if I put one typo, I am in good. But it's amazing that you can do such a computation, and also amazing that at the end, using unitary action in some sense is not necessary. So this at the end can be, provided by algebraic geometry. And now a beautiful variation, I think. I learned these things by Antonio Lerario, but it's quite beautiful. If f and g are real, you can define the same as above, but now computing over the real. This is called Fubini study real. It's a different integral, but still is invariant by the action of the orthogonal group. So you can ask, is maybe Bombieri-Weil because it's invariant? And the answer is no. The answer is no, because two monomials are now no more orthogonal, because over the real, for example, if you compute when the exponents are even, this is clearly a positive function and cannot have zero integral, no? So it is different from the previous one, and then you can enjoy. And in the exercise sheet, I put some exercise computing these, even for matrices is non-trivial. Something remains true, that according to these, the sum of harmonic decomposition are still orthogonal. And let me, how much time? No, I have 10 minutes because there are some, I think all you are tired. So in the last slides, I want to show something really exciting, that the integral of real Fubini study and the same in the complex situation have a probabilistic interpretation, because when you have a measure, you can measure the set, and then you have a probability distribution on the space of real polynomials. And in particular, you can measure volumes. No? And so the idea is that when you have a scalar product, and you see I introduced many of them, the Bombieri-Weil, the variation with I, the real Fubini study, and so up to some scalar, you just multiply, you take an exponential of this and you define a measure and you get exactly the same as above. And so you get the probability distribution of a polynomial. So what happens that at the end, if you compute the volume according to this, F alpha comes just to have a Gaussian normal distribution for each, sorry, here is F alpha is the typo. But then you have to put this Gaussian all together. So this Gaussian have a variance. And let me show a beautiful story. The Bombieri-Weil amounts to this variance. And what's the basic question about probability if you want to study real polynomials? How many real roots you have, no? It's, you pick a number D, now we will pick a random F, the polynomial homogeneous in two variables, so it's, and the question is how many real roots? You should have the expected values, which is of course a number between 0 and D. Maybe it's not well known, the story, it's very beautiful. The first who studied this is Mark Koch, who wrote a pioneeristic paper studying these Fi, Xi, and he put just a normal Gaussian who when all Fi goes in N01. And his paper is a masterpiece of computation of integral, and he showed that this expectation grows as logarithm of and grows when the D goes to infinity. So you see the answer is that the polynomial with many real roots are few. It's a logarithm grow very, very slow. What's the defect of this computation? And that this
for this computation, a priori, it could be half the polynomials have D and half of them have 0. Or, sorry,
that's correct.
No, not half. Sorry, no.
But of course, this is not true because
D over 2.
You are clearly chambers in the space of polynomials. All these are open with the positive measure. Positive measure, and what you are doing is computing the weighted average of these. Okay, so this distribution is not orthogonal invariant. So it is absolutely not a natural choice. And it's quite strange that in the time of Mark Koch, nobody understood this. So sometimes after things are studied first, you get a different understanding. Why I wanted to insist that if you have a different scalar product, you can have different results. Here, you get different answer. If you take everything according to Bombieri-Weil, First, this was done by Shabbos-Meir, and this answer, I think, is well known. The square root is called in the people who study these things the square root principle. You see, the answer is completely different, and now the measure is that is much more big. The volume of polynomials with the sum real roots is completely different than the logarithm, and the surprise is that this number is exact. It's not an asymptote. They compute this, and Edelman-Kostland rewrite this with the geometric proof, which is really, really beautiful and easy with the geometry of rational normal curve. You can prove this. And let me make some advertisement of this paper by Lerario and Lamberg. They do the analogous computation for the real Fubini study. And this is the answer. Sorry, it is, you see, it is for the Bombieri-Weil is square root of d, and the other is square root of d plus 2 over 3, which is much larger, you see. When d increase goes essentially linearly in d. And I think this is probably the maximum among all the possible probability distribution. I think this is spectacular. As one of the basic questions in mathematics is computed the zero of a polynomial, and so how many are reals is a basic question, and these things should be, I mean, really more well known, and they come from essentially different. So in the exercise sheet, you can compute real Fubini study versus Bombieri-Weil with different situations. The case of matrices, for example, is not obvious. And I have 1 minute. So you see, I started with the Segre. I studied more the Veronese because there were more things to do. And this is the more general case. It's called Segre-Veronese, or partially symmetric tensors. And let me just state the result. Even here, you can classify all the possible invariant metrics. You still get a polyhedral cone. And the requirement is this one. But now, since you can mix the power, you have a lot of these, depending on indices, I1, Ik, and each I1 arrive to the degree of the power of V1 and so on. So if in the first case, all the I are 1, all the possibility are only 0, and you get just Bombieri-Weil. And in general, this gives the definitive answer for all the invariant metrics, and Bombieri-Weil correspond to 0. And again, this space splits in a lot of harmonic summands due to the harmonic decomposition. I think Ettore, where is Ettore? You will see later. He was a DC of Poema, and he will speak about his experience this afternoon. In his doctoral thesis, studied exactly this decomposition in this space in a slightly different pattern. Let me skip the proof. I want to finish in time. Thanks. Question?
Yes. I have 2 questions. So first, can you go back to the slides where you showed this SL2 invariant?
Oh, yes. Only for binary.
Yeah, for binary. this formula, the last slide, this is the Bombieri length of the wedge, right? As you mentioned. So do you have like any connection? Semantic wedge product. If you take, let's say, log powers of one.
Yeah, of course. If you have SL3, you can get something analog with wedge 3. But then it's not a scalar product. You have a FGH. So it's partially extendable. What you're asking for ternary forms, for example, for quartic ternary, there is the famous cubic invariant, which is exactly you're asking, but it's not a scalar product. So it does not give a distance, it does not give well, if it gives a measure, could, I'm not sure. That's interesting. Maybe I understand why you asked. Oh. I never thought about it. I don't know. If, because anyway, it's a measure difficult to be studied because it does not come from a scalar product. No.
Another question is that for real potential, it's fast. But if you push all the weights which are harmonic component, I think it's not realized. If you look at the singular product,
of course.
Then
well, that's a correct. I forgot to tell. But it's degenerate, yeah, so it's a bit.
The idea is if you perturb it, maybe like all the weights sit there, then another one's in the picture of the polyhedral cone.
Yeah, Kazgali said that in the polyhedral cone, you just take the edge of Bombieri-Weil over the harmonic. So of course, there you have the Chebyshev polynomials, and all of them have d real roots. So the chamber is essentially only one. There it's if you pick any random there, the answer is always d, and the average is d, and that's correct.
And for some small perturbation, other components.
Okay. That's correct.
So there is no maximum.
There is no maximum in the non-degenerate. Good. Thank you. I forgot. I knew such a thing, but I forgot. Beautiful.
Monique has a question online. Monique, can you hear us?
Yes. Can I ask a question?
Please do.
Hi, Monique.
Hello, Giorgio. Thanks a lot for the very nice lecture.
And
so
you nicer, yours.
So I just want to make a small question and a comment. So this inner product on polynomials, I guess you can also, the Bombieri-Weil is also, I think you said it, that it can also be alternatively defined via integration on the unit sphere. I speak of in the real case. So the inner product between two polynomial Fg is equal, up to a scalar product, a scalar multiple, to the integral Fg on the unit sphere, where you equip the unit sphere with a Haar measure, which is invariant on the rotation. So that's a thing you have said, I think, yeah? Correct?
Yes, correct. Yes. Well, essentially, it goes down to Fubini studi, real Fubini studi, I think, no? What you... Yeah.
Exactly. So what I wanted to mention also is that this harmonic decompositions of polynomials plays a crucial role in the analysis of the SOS hierarchy for polynomial optimization on the sphere. So this is a key ingredient that is, one of the key ingredients which is used in the analysis of Fang and Fuzzy, where they show that, so I define the SOS bound of order T, say, and the distance to the minimum of P is in order 1 over T square. And one of the keys to show this is to use these harmonic decompositions of polynomial on the sphere, combined with other things like the polynomial kernel method and so on. But so I just wanted to point out these very intimate links with the tools that you are explained in your lecture for analysis of polynomial optimization. So thank you.
Thanks, Monique. If I remember correctly, also in the analysis by Greg Beckerman of the difference between sum of squares and positive polynomials, it uses this inner product.
Yeah, also, that's correct. Yes. So then that would connect to the what Giorgio was explaining about volumes of subset of polynomials. Yes, correct. Yes, thanks, Didier. Yes.
Bernard.
If we are interested in the skew symmetric tensor, what
In the two symmetric
skew symmetric,
skew.
anti-symmetric. So do we have a similar?
Well, there is I think the wedge K of V. Let me. Is irreducible even for SO and also for SQ, but
Yeah, you need to
for
use
both.
symplectic group.
Yeah, for the symplectic group, it splits. Indeed, there is a harmonic decomposition of these according to symplectic group, which give a analog theory of symmetric for orthogonal. And so there is a unique choice. So the answer is the following: if you have P and you have a Q here, and you have S orthogonal group, sorry, Q is in S2. And you have the orthogonal group according to this Q. And there is, you can call that skew symmetric Bombieri-Weil, and exists a unique Q Bombieri-Weil in Sim2 of wedge KB. And this is unique, and the explicit is the determinant of a gamma matrix on the composable. So if you have V1 VK and double V1 double VK, you construct a big gamma matrix when you multiply, I think, Q. No, okay, this is in orthonormal coordinates, but it's easier. The Q Bombieri-Weil of this is just the determinant. Now, the problem is that you have not only, okay, yes, I guess. Yeah, you have a Q, VI double VJ, you write down the right, and then they compute the determinant, and this gives the answer. Yeah. Yeah.
Okay, time for lunch, I guess. Thanks again.